All right, so let us talk about why we are even making you do student presentations in the first place. Okay. Um, the thing is, as over your life, you don't know what kind of like paths you're going to take in your career. For example, some of you might decide to do a master's and continue to do a PhD, and then go into academia or research or even industry. You may decide to do that. Some of you may decide to not continue on physics because you didn't find it all that interesting. But maybe you go and decide to do some other subject. Maybe you guys decide to do an MTech in something. Maybe even decide to do an MBA and get into management. Maybe you'd specialize in something else. Some of you might not even decide to continue on college. Maybe after this, you will write your government service exam or your UPSC exams, or maybe some banking exam or something like that. And maybe you'll go and do, maybe you'll start a career. All of these options are open to you. But at some point in your life, you're going to have to stand in front of a group of people. Maybe you'll have a PowerPoint presentation, maybe you won't. And in front of that group of people, you're going to have to present something. Either you're going to present something on a topic, or you're going to have to present something about yourself. Those situations will be when you do like a college admissions. For example, Ayush and Ganesh, in a few months, most likely they'll be standing in front of a group of teachers and giving their entrance viva for college. Some of you will have to do it for a job interview. Some of you might have to do it for a PhD defense. Some of you might have to even do it for a job presentation. Whatever your course in life will be, at some point of time, you will be in a situation where you have to speak in front of a group of people who will be asking you questions. When that happens in your life, the last thing you want to do is say to yourself, I have never given a presentation before. I don't know what I need to do. So this is the fundamental object of this class. More than physics, more than like making all of these groups and all that nonsense. The fundamental idea behind this class is to get you prepared for the one time in your life when a presentation will truly matter. And to give you an example, for those of you who are in second and third year, you'll remember that last January and February, last year's January and February, I gave 2 presentations in college. Those 2 presentations are a big reason behind why I got hired in this June, July. Okay, those presentations are sort of like my job interview. Okay, so it does matter. And sometimes it matters, it leads you to a job, like it led to my case. Sometimes it's going to lead you to a promotion, because in a lot of like high-level promotions, you actually have to give a presentation as to why you should be the one promoted. Sometimes it leads to, sometimes you have to do it in your PhD defense or in your exam. But no matter the case, you're going to have to do it once in your life. Now, here we're making it slightly easier. You're going to work with a group of people, so all the pressure is not on one person. You can split up the jobs. And then obviously, because this is a physics thing, you're going to have to do it on something on physics, right? But this is the fundamental idea behind why we're making you all do this. So instead of seeing this as something that, an extra annoying piece of work that you have to do, and yeah, maybe it might be annoying, I can understand that. See it as some sort of like see it as something where you have a low stakes presentation, right? You can make mistakes here. You can sort of do things incorrectly here. And then you can learn from here. And later on in life, when you actually have to give a presentation for something that actually matters, you at least go, okay, I know what to do here. I have already been in this situation before. All right. So this is the idea behind why we're making you do this. Now, today's class, what we're going to do is, first of all, I am going to give a sample presentation. I am not the greatest presenter in the world. I am very, very average, but I do know the basic idea of how to present. All right, so I'm going to give a brief sample presentation. It is going to be a repeat of my presentation and test. So if you guys have already sat through that, it's going to be a repeat of that. I'm sorry, but this time at least I'll have more time. Last time I only had 7 minutes to talk about the whole thing. And then I will, not only that, I'm also going to go into how I prepare for presentation. How do I do the research, how I construct my presentation. So for those of you who have never done a presentation like this before, at least I will show you some guidelines on how you can go about working on it. And finally, I'm going to talk about evaluation because it is a little bit detailed. It's not as straightforward as you might expect. So before we start the presentation, do you all have any questions that you'd like to ask?
None, sir.
Okay. Just give me a second to set up. All right. Okay, can you let me know if you are seeing the slides on the screen, if it's full screen?
Yes, sir. It's fine.
All right. Okay. So good morning, everyone. My name is Vikramjit Chandra, and today I'm going to give a talk about the detection of phosphine in the Venusian atmosphere as it was released back in September 2020. So this talk is not going to be a very technical talk. It's going to be a relatively low-level talk. And one thing that I should warn my viewers is that I am not an expert in planetary astrophysics. So a lot of the more technical aspects of what was done here is a little bit beyond my understanding as well. However, back in September 2020, so this is just a little shy of a year ago, Greaves and her group released this paper on the Astronomy Archive. And basically what this paper says is that they had made a small detection of phosphine gas in the middle atmosphere of Venus. And you should note that we do not expect there to be any phosphine in the Venusian atmosphere. So they had made what we'd call a very, very surprising detection. They were very confident of the detection, and they also could not explain where the phosphine gas was coming from. So after they released this paper, there was a huge amount of buzz in the astrophysics community. And once the mainstream media got a hold of that, once the mainstream media got a hold of this paper, we started to see headlines like this. And you may have seen some of these headlines last year, that maybe somebody has detected life on Venus. So here now what I'm going to talk about is how the detection of phosphine gas. See, remember, they're detecting phosphine gas. They are not said we detected life on Venus. All they've said is we've detected phosphine gas in the atmosphere of Venus. So from how do we go from the detection of phosphine gas to possibly to be it being a sign of life? All right. So here what I'm going to do is I'm going to talk about whether it's possible for there to be life on Venus, why the detection of phosphine gas is important. We are then going to briefly analyze the paper that Greaves had released back in September, and then we're going to talk about the fallout of that paper. So first thing, is it possible for there to be life on Venus? On first glance, Venus is, at least the surface of Venus, is one of the most inhospitable regions in the solar system. On the surface, the average pressure is about 92 times atmospheric pressure. So it's 92 times more pressure than what we have here on Earth. Secondly, the surface temperature of Venus is easily over 450 degrees centigrade during the day. This is one of the hottest surfaces. This is the hottest terrestrial planet in the solar system. It is hotter than Mercury, which, if you remember, is pretty close to the sun. On top of that, most of Venus is made of carbon dioxide. It is a 96.5% carbon dioxide atmosphere. So at least life as we generally know it most likely will not exist there. In fact, when they sent probes in the 70s and 80s, the probes which survived the landing would only survive for a few hours before the temperature and the pressure completely destroyed them. However, in the middle atmosphere of Venus, the conditions are not that bad. Up around maybe between 40 to about 60 kilometers from the surface of Venus, the temperature is between 30 to 60 degrees centigrade, so it's not too hot. The pressure is between 0.5 to 1 atmosphere, and that's not too bad either. So it is possible for some microbial forms of life to exist over there, right? Of course, one thing is that is the area where Venus has clouds. On Earth, we have clouds of water vapor. On Venus, there are clouds of sulfuric acid. It literally rains acid on Venus. So if there is a microorganism that is existing on the atmosphere of Venus, it has to deal with all that acidic environment. But that is a problem. But that is something that even microorganisms on Earth can survive in, right? Now, the idea of like there possibly being life in Venus is not a particularly new idea. The oldest paper, some of the oldest talk about this I could find was as far back as 1967. Carl Sagan himself co-wrote a paper with Morovitz about the possibility of there being life in the clouds of Venus. On the left-hand side here, I have a more recent paper from 2018, where they actually talk about all of these possibilities. So is it possible for there to be life in the atmosphere of Venus? It is. It's going to be microbial life, not life like us, but tiny cells. But it's kind of possible if they exist. Now on the right-hand side here, we are now going to talk about why phosphine could be a signature of life on a planet. And this is a paper by Sosa Silva, who, by the way, is also a co-author for the Greaves paper, where they put forward the argument that phosphine is a very, very good biosignature gas. So what is a biosignature gas? If you study the gaseous composition of a planet's atmosphere, a biosignature gas is a gas that, if it exists in the atmosphere, could possibly be a sign of life. A very obvious example of a biosignature gas is oxygen. Another example of a biosignature gas is water vapor. In this paper, Sosa Silva put forward the very, very strong argument that phosphine can be another biosignature gas. And why that is because it is very rare for phosphine to be produced naturally. When I mean naturally, I mean abiotically. See, phosphine can be produced by volcanic activity. It can be produced by lightning strikes. It can be produced by what we call the photoelectric dissociation. The sunlight will dissociate a molecule and then create the phosphine molecule. But naturally, phosphine molecules do not it's very difficult for phosphorus to convert into a phosphine molecule, because in general, phosphor would rather convert into a phosphate molecule, right? So in terrestrial planets, we actually do not find any phosphine except for one planet, and that planet is Earth. And the reason we have phosphine on Earth is because of human activity, agricultural activity, semiconductor industries, all of that produce phosphine. But the other source of phosphine is anaerobic microbes. So the detection of phosphine could possibly be a detection of microbial life. And this is why there was a lot of excitement when this paper came out, because the detection of phosphine at Venus could possibly mean that microbial life existed on Venus, since they would be the ones which would be giving out the phosphine gas. Okay, so hopefully now I've explained why the detection of phosphine was so exciting to a lot of people, and why people were suddenly talking about the possibility of there being life on Venus, even though the life is like very, very tiny microbes. Now, Sosa Silva's paper was actually for exoplanets. Exoplanets are planets that are rotating around other stars. And for those of you who attended my talk on exoplanets, one of the biggest pushes right now is to try and characterize exoplanets where life could possibly exist. So there's a whole bunch of work being going on biosignature gases and signs of life on exoplanets. Now we will talk about the paper of Greaves herself. So what Greaves and the group did was they used something called the JCMT. The JCMT is the James Clerk Maxwell Telescope. This is a radio telescope out in Hawaii. And in June 2017, they made 5 observations of the atmosphere of Venus. They observed the planet of Venus, and they took readings from the atmosphere. And what they were doing was they were taking spectroscopic readings of Venus. What a spectroscopic reading means is that the atmosphere of Venus is going to radiate out electromagnetic waves. And they are going to be at different frequencies. These guys are looking at the radio frequency. Now, depending upon the chemical composition of the atmosphere, the spectrum will have certain absorption spectra. At certain points of time, you'll see a dip in the incoming signal. And the exact frequency at which those dips happen will tell you exactly which molecule or which chemical element is causing that dip. So here is the discovery that they made, is that they found this dip over here, this very tiny dip over here, and that they said correspond to a dip at 1.123 nanometers, which is a sign of phosphine. Right? Now, first of all, I'm going to tell you this is not a very convincing graph. This thing over here that you see, these other things over here, this is the background, or the background noise. And here you can notice the background noise is something like 10 to the power minus 4, and the dip that they're noticing is something like only 2 times that size. This is what we'd say when the signal to noise ratio is very, very high. And honestly, it doesn't look very convincing. However, they did do some analysis, and they tried to figure out what the concentration of phosphine would be that would cause a dip that looks like this. And based on the analysis, which is given here, this is their this red line basically represents what their expected concentration of phosphine is. Based on the analysis, they expected phosphine to be 20 parts per billion, okay? Which is a very tiny quantity, but it is not a non-negligible quantity. It is a significant amount from the expectation from a Venusian atmosphere. But they knew the data was not very good. The signal to noise was very, very high. So what they did was they tried to ask time on the ALMA telescope. The ALMA telescope stands for the Atacama Large Multi-Millimeter Submillimeter Array. This is a telescope set in the Atacama Desert in Chile, and it is probably the most famous radio telescope in the world, at least in astronomical circles. And they managed to do an observation of Venus on March of 2019. So now we have jumped forward 2 years after the initial observations. So in 2019, they did some observations, and this time they got a much better signal. Now here you can clearly see the background, and here you can clearly see the absorption depth. This is the absorption depth that they said belonged to phosphine. They did the analysis. Again, they reconfirmed their readings that the phosphine concentration was 20 parts per billion. And on top of that, they were saying that based on the analysis, they had a 15 sigma confidence in the results. In science, specifically in physics, if you have a 5 sigma confidence or above, it means that the results are valid. It generally means that you have a very, very strong confidence that the results are valid. So they were reporting 15 sigma, which is very, very high. Right here, we have the signal strength at various latitudes. This is the red line corresponds to the signal strength on the equator. The blue line corresponds to the signal strength in the mid latitudes. And this black line corresponds to the signal strength in the polar regions. The signal to noise ratio for the polar regions and the equator is not very good. But that was not a big deal because most of the observations were in the mid latitudes anyway. So overall, they're getting like a signal to noise ratio of about 13, which is very, very good. All right, so now that we know that they had the detection of phosphine, the next thing they needed to do was try and explain where the phosphine gas was coming from. So you can't just detect phosphine in the atmosphere and say, hey, you found a sign of life. You kind of need to exhaust every other avenue that is possible. So first of all, they tried to ask themselves whether the phosphine was coming from the surface of Venus. And then they said that it's probably not possible because we have sent probes on the surface of Venus and we have not found any real deposits of phosphine or phosphate minerals or anything of that sort. And like I said before, even if you do have phosphorus on the surface of Venus, it will most likely form phosphates, not phosphine. Next, then they tried to work out all the possible ways that phosphine would be created in the middle atmosphere. So they took all the possible chemical reactions that would allow it to happen, all the possible photochemical reactions that allow it to happen at different pressures, at different temperatures, and then they sort of made up a rate of the formation of phosphine. So this red line here tells you what is the rate of the formation of phosphine gas from abiotic processes. Abiotic here means non-life, non-biological processes. And you can see this is at different heights. Next, they also calculate what the rate of destruction of phosphine would be. Like I said, phosphine is a molecule that is very easy to break apart. The solar rays can break it apart, other chemical reactions will break it apart, so on and so forth. So what they noticed was the rate of destruction of phosphine is much, much larger than the rate of formation of phosphine. This scale at the x-axis is a log scale. So the rate of destruction is at the minimum 10,000 times greater than the rate of formation. So if they are detecting phosphine in the atmosphere, something is producing it. And as far as they know, it is not like a geological reason or a chemical reason. There is something new that is happening, something that they could not account for. So finally, what they said was they were confident that it was phosphine because they had used 2 different telescopes to look at it, and that used different processing methods to figure out the results. So they explain why they think it's phosphine. And then they say, fourthly, there is no other known reasonable candidate transition for the absorption other than phosphine. This is going to be a very controversial statement, and I'm going to talk about it in a little bit. And finally, they conclude by saying, even if confirmed, we emphasize that the detection of phosphine is not robust evidence for life, only for anomalous or unexplained chemistry. So basically it's saying, hey, we are not saying that we found life. We're just saying that there's something that we can't understand happening here. Obviously, the media completely ignored it, and then they talked about how maybe we detected life on Venus. Right? So this was the condition when this was like what was going on when they dropped the paper in 2020, in September 2020. And almost immediately, every astrophysicist looked at it and went, wait a second, something's not right here. And there were a lot of reply papers. So before we talk about the replies by the astrophysicists, and I'm going to specifically focus on one paper, I'm going to talk a little bit in more detail about the basic method they're using to detect phosphine. So basically what they're doing is they're taking the radiation from the atmosphere of Venus, and then they are decomposing it by using a Fourier transform. So those of you who have done Fourier series and Fourier transforms, This is one of the things we use it for. They decompose the signal to see the power at various frequencies. And since these are electromagnetic waves, you know that if you know the frequency, describing a wave in forms of frequency or wavelength or energy is basically the same thing, right? Because you can easily convert from one to another. So you decompose it into various frequencies or various wavelengths. And basically what they are saying was they found an absorption spectrum. So you notice there's a drop in power over here, an absorption spectrum that they attributed to phosphine. The problem is there is sulfur dioxide also has an absorption spectrum very, very close to this absorption spectrum of phosphine. The difference is 1 megahertz, which is very, very small. Okay, in frequency terms, the difference is only 1 megahertz. And the problem, of course, is sulfur dioxide is the third most common compound in the Venusian atmosphere. So the big question people were asking is, how do we know that it is a phosphine energy dip and not a sulfur dioxide energy dip? Because you see the instruments they're using, they have something called a resolution. Okay, and the instruments were not good enough to resolve between these two differences. What they were seeing was this. This is what they were saying. This is what they were observing. And they were saying, hey, all of this is due to phosphine. But what we need to know is exactly how much of this is due to sulfur dioxide. And if there's any left, how much of that is due to phosphine. Right? Now, Greaves and all, they know about this. They know sulfur dioxide is the third most common element, common compound. They know that there is an absorption spectrum of sulfur dioxide very close to what they are seeing from phosphine. So obviously they tried to work it out. So what they did was they made an observation at a completely different wavelength. This is at a frequency of roughly 267.54 gigahertz, as you can see here. Here, sulfur dioxide has another absorption spectrum that you can detect, but phosphine does not. Okay, so here they expected to see only a signal from sulfur dioxide. This black line is their background signal. This very dark black line over here, right over here, that is their detection of sulfur dioxide. And as you can see, it is basically nothing. They do not see any sort of real absorption. So based on their observation, they tried to estimate the best case concentration of sulfur dioxide, and that is given by this dotted red line over here. Okay? So this is based on the concentration, on the impurities, and on the limitations of the instrument. They say this is possibly the highest possible concentration of sulfur dioxide, this dotted red line. The solid red line is the concentration of sulfur dioxide required to completely explain the dip they noticed. So if the dip they noticed was entirely due to sulfur dioxide and not due to phosphine, then it should have looked like this big dip over here. But on the other hand, they only get this small concentration. And the figure on the right-hand side will be perhaps a little bit more clearer. This red line, as you can see, is what they had observed. This is the dip that they're attributing to phosphine. This green line is what they're saying is the contribution by sulfur dioxide. So according to them, the contribution to this dip by sulfur dioxide is only 10%. Everything else is coming from somewhere else. And according to them, that somewhere else is a phosphine gas molecule. This is all in the original Greaves paper. But this is the part that was attacked the most, because a lot of people believe that the analysis of this specific sulfur dioxide contribution was very, very, it was not very good. So as soon as like a month later, Villanova and all put out their group reanalyzing their data, where they put out where they saw a lot of issues. And in November, 2 papers came out, one by Snella and her group, and another one by Thompson. And all of them basically also had a lot of doubts about the accuracy of this analysis. But the paper I'm going to talk about is by Linkowski and their group. And this paper came out in January 21. So this came out just like a few months ago. This is the paper that basically killed the original Greaves paper. And what they did was they basically used a computer simulation to simulate the atmosphere of Venus, right? And once they simulated the atmosphere of Venus, they sort of started asking, okay, what kind of absorption spectrum would we see, right? And here there are 4 different simulations for different concentrations of phosphine and sulfur dioxide. So I'm going to have a look at the number B over here. This is the second one. VIRA stands for the Venus International Research Atmosphere. Sorry, Venus International Reference Atmosphere. this is basically the most accurate and up-to-date data on the atmosphere of Venus. So based on this, what they said was, okay, if we do a computer simulation, we are getting the exact same observation that the Greaves model was getting. So that's fine. The observations are fine. But they also did a look at the absorption spectrum. And according to them, sure, if phosphine existed, yeah, there will be an absorption spectrum, as you can see here. But you should also detect sulfur dioxide. And not only should you detect sulfur dioxide, which is this big dipole here, not only should you detect sulfur dioxide, you should detect it at least 2 times stronger than the phosphine detection. Remember, Greaves and all said that the sulfur dioxide contribution was only 10%, which means 1/10 of the total phosphine contribution. But these guys are finding that their contribution of sulfur dioxide should be 200% minimum. And in fact, if you look at the D graph over here, they notice that if you completely remove phosphine, you can completely explain their observations by sulfur dioxide alone. You just need a higher concentration of it, just a higher concentration than what was expected. So this one was a big, so here you can see that their observations can be completely explained without having to introduce phosphine gas. And the second one, and the one that actually killed the entire thing, was something called a radiance mixing model. So what they said was, okay, you have a certain incoming signal. It has a certain amount of strength. Using the strength of the incoming signal, let's try to find out exactly where in the Venusian atmosphere the signal is coming from. You have to remember that Greaves and all, they were saying that they were detecting phosphine gas at 56 kilometers above the surface of Venus. What Linkowski and the group found out was that the signal that they're observing could not possibly come from 56 kilometers above the surface of Venus. It had to come at least 80 kilometers above the surface of Venus. Whether it was sulfur dioxide or whether it was phosphine, it could only come at least 80 kilometers above the surface of Venus, if not more. And this completely kills the idea that it could be phosphine. Why? Because at 80 kilometers above the surface of Venus, the atmosphere of Venus is so thin, it can no longer block out the strong solar rays. So the sun gives out gamma rays, X-rays, ultraviolet rays, all sorts of charged particles and things like that. And Venus, at the middle atmospheres, the upper atmosphere basically blocks out most of it. But once you go 80 kilometers above the surface of Venus, the gases over there are completely exposed to these very, very powerful solar rays. And what happens is those rays will completely destroy the phosphine molecule. So if you look at this little graph over here, you see this little dotted violet line. This is the estimation of the concentration of phosphine gas according to the altitude. And you'll notice that the gas completely stops existing above 70 kilometers. There is absolutely no way phosphine gas can exist above 70 kilometers on the Venusian atmosphere. On the other hand, sulfur dioxide has a much more robust chemical composition. The atomic bonds between the elements are much stronger. So you can see here this little green line here, that gives you the concentration of sulfur dioxide at various altitudes. And as you can see, it is possible for sulfur dioxide to exist above 80 kilometers. So based on these two results, they concluded that they had not detected phosphine gas. What they had done was they had detected sulfur dioxide from the upper atmosphere. And finally, they also explained why the original Greaves group could not find any sulfur, found very little concentration of sulfur dioxide. It is a result of something called line dilution. Line dilution is a source of error that happens in a lot of telescopes, especially radio telescopes and telescopes that look at low frequency, telescopes that look at low frequency electromagnetic waves. Line dilution basically means that the signal is smeared out across various frequencies. And it is something that ALMA particularly suffers from because ALMA has a completely different system of taking in data. Now, obviously, this is something that people know, and you're supposed to account for it in your models. What Greaves and all had done was they had severely underestimated the amount of line dilution. They estimated that the line dilution was only 65%. Linkowski and all said that that is wrong. Your line dilution is something like 95%. So they actually took Greaves' data and they recreated what the expected sulfur dioxide signal is, and then they noticed that it is exactly what is, and it is exactly enough to account for the phosphine signal. So the reconstructed, corrected sulfur dioxide signal exactly accounts for the phosphine signal. So as of now, while the idea of there being a phosphine detection in Venus caused a lot of commotion and a lot of excitement, as of now the idea is dead. And aside from a few follow-up papers, that's basically the end of the story. So I'd like to thank you all for sitting here for my presentation and suffering through it. Maybe some of you did suffer through it. Here are the references that I used, and if you have any questions, I will take them now. All right. And if you do have questions, please use the microphone, because as you can see, I'm not looking at the meet right now. Any questions?
Any advantage, sir, like finding? So is there any advantage of like phosphine, sir? Like if there is existence on Venus, sir?
Yeah, if phosphine exists on Venus, we have to explain where it came from. And the thing is, we don't expect that to be phosphine, because there is Venus does not really have lightning strikes or volcanic activity or anything like that. So if phosphine exists in Venus, it is possible that it could be caused by life. That is why there was so much excitement. Phosphine, as I said, if you detect it in a rocky planet, it could be a possible sign of life. That's why phosphine detection is always met with a lot of excitement. That is, of course, only in a rocky planet. On a gas giant, it's a completely different story. Like we have detected phosphine on Saturn, but that is completely due to the internal activity within Saturn's atmosphere. So yeah, phosphine detection on a rocky planet could possibly be a sign of life. On Earth, at least, all the phosphine we see in the atmosphere, that is almost entirely due to biological activity. Any other questions?
Sir, what is this background signal, or what you said, a background noise?
So you're talking about something like this, right?
Yeah. So
yeah, this is the background signal.
Acha.
So you'll see something like, I think Rebecca's graph is much better. Yeah. So you'll see something like a background, and then you'll see the dips at certain frequencies or certain wavelengths. You'll see the dips. Aside from that, it's just like a solid background signal.
Okay.
Any other questions? Okay, so let me close out this presentation for now, and let's go back to our class So this is an idea of how you would want to make a presentation. I didn't time myself. I don't know how much time I took. I think I took maybe 20 minutes or something. But hopefully, now you sort of have an idea what you want to present, how you want to set up your slides, how you want to present, and what you want to do. So now, do you have any questions about the way I did my presentation? Not the material in the presentation, but the way I did my presentation.
Please feel free to ask. Don't feel shy. This presentation thing is in your curriculum now, okay? It's a compulsory thing. So please ask if you have any doubt, anything.
Okay, just a second.
All right. We're supposed to explain it like in this detail, sir.
Sorry, could you repeat your question?
So, like, are we supposed to like explain it on detail, sir? Like you did.
I mean, I did, yeah. It's going to depend exactly what you're going to talk about, yeah. But you're supposed to sort of explain like a little bit of what's going on. Hopefully, I kind of explained like some of the physics that was going on here, right? See, I can't just go, hey, they detected phosphine on Venus. Maybe it leads to life, but then here's another paper that said, hey, there's no phosphine on Venus. And if I don't explain what the graphs mean, why they thought they detected phosphine on Venus, and then why other people thought that they did not detect phosphine on Venus, I have to sort of explain all of that. I can't just say they detected phosphine on Venus, it was a mistake, and then end of story. That's not like explaining the physics behind it. Here I'm talking about like the sort of the analysis that they did. And Obviously, I didn't talk about the analysis in detail. I didn't go through the mathematics, for example. That is kind of high-level stuff, and it's going to be a waste of time. But at least I actually like showed you the graphs, and I explained what they were doing with the graphs to give them the conclusions that they had in the paper. And then I was talking about how other people analyzed those graphs, made a different set of conclusions, and then they showed that the original conclusions were wrong. So you kind of need to sort of explain that in detail, yeah. I think Rudra was going to ask a question. Were you going to ask a question, Rudra? You got completely cut out. Can you repeat yourself? Okay, I can't hear. Just type it out in chat, okay, if you have a question. I couldn't hear it from your microphone. Okay.
So,
Yeah?
so,
Yes, go ahead.
so like when we are giving the, like when we are submitting, so when we are submitting the topics which we are presenting, sir, to you guys, sir, at that time, like we give a little description of what we are giving, like what
Yeah,
we are
you have to
presenting,
give
or
an
like we
abstract.
just
I will
write
give
a
an,
topic.
actually, I'll show you the abstract for my presentation. Hold on. So when you submit, you're going to have to submit 2 topics. First is the talk of what your talk is about. And then here's my abstract. A discussion on the detection of phosphine gas in the middle atmosphere of Venus, as reported by Greaves et al. On September 2020, and its ramifications in the search for extraterrestrial life. We will also discuss the fallout of the paper, specifically the response by Linkowski et al. On January 2021, which showed that the detection and subsequent analysis of the original paper was flawed. This is basically a summary of what I just talked about. Okay, so yeah, you're going to have to give an abstract that looks something like this. Where you're going to actually talk, you're going to talk exactly the scope of your presentation. So let me give you an idea. Let's say that your topic for your presentation is black holes. Okay? If you say, sir, we want to talk about black holes, I will immediately say no. Why? Because black holes is a huge topic. I could probably give a 1-hour talk on black holes, and it'll not even cover most of the things. It'll just give you a very basic introduction to the subject. But let's say you come up to me and you say, sir, we want to talk about the photograph of the black hole that was made in 2020. And by the way, they have made an even better photograph now. They've made a much more higher resolution photograph. So if you want to talk about the photograph of black holes, I will go, okay, yeah, you can talk about that possibly in 20 minutes. And then you will write, that you're going to discuss about the picture made of black holes based on the paper by, I forgot the names and things like that. Let's say that you say that, sir, I want to talk about wormholes. All right. Again, I'm going to be like, maybe not, because wormholes is like a very, very big topic. But let's say that you want to say, sir, I want to talk about wormholes, like how Einstein and Rosen originally discovered them. So it's only 1 or 2 papers. Then I will be going, okay, that sounds like a much more reasonable thing that you can do in 20 minutes. See, your presentations are going to be 20 minutes long. You can't have a vague topic. If your topic is like artificial intelligence, that is a very vague topic that someone can easily talk for 2 hours for. But if you're going to be like artificial intelligence being used in data analysis of astronomical data, that is a short topic. Okay, so this is why we want you to have an abstract. The abstract will tell you exactly how much material you're going to cover, and based on the abstract, I will know whether your presentation is going to be long enough or if it's going to be too long or things like that. Right? It also means that you can't just like pick up a word like black holes and put it there and say, sir, we're going to do it on black holes, and then you don't bother doing any reading until the day before the presentation. The day before you pick your topics, all of you have to sit together as a group, decide on like 2 topics, do a little bit of reading, and then be like, okay, these are the specific subtopics that we're going to cover in our presentation, and maybe we will do it in 20 minutes. Does that answer your question, Sean?
Yes, sir.
Okay. Any other questions before I move on? Oh, yeah, Rudra, 1 second. Okay, Rudra had the question. We will have 1 presentation and 3 people will talk on it. You may have 1 person talking on it. You may have 2 people talking on it. You may have 3 people talking on it. I will talk about the distribution of work in a little bit. Okay, I will talk about that in a little bit. So we'll just answer your question in a little bit. Now, I know I cut someone off. Could you ask your question again?
No, sir. I was going to talk. Like I was going to tell you about Rudhanan's questions.
Okay, okay. All right. So now I'm just going to give you a brief talk. Yeah, sorry. Go ahead, go ahead.
Sure.
Sorry, Adish, your mic is sort of lagging. Can you repeat your question?
Research on the top.
Do you need to do research on topic? Yeah, you need to do some, like you do have to read up on the topic. Is that your question? Because half your question is getting cut off for the mic. If you don't mind, can you just type it out properly in chat? Because I don't think I answered your question properly. Just type it out in chat. Your sort of sound is getting, there's some interference in your sound. Okay, so now I'm going to chat a little bit about how you prepare for a presentation. Okay. Now, in a presentation, in generally, there are three sort of categories you do work in. The first category is what we call research. Research is where you basically, once you've thought of a topic, once you picked a topic, okay, wormholes, for example, let's say you picked wormholes as a topic. This is where you collect the relevant materials. You go on Wikipedia, you read up on wormholes. You look at the papers about wormholes. You know, you download them, you read through them. You read some additional material. You just basically collect the data that goes into it. Maybe you go on YouTube and you watch some videos about wormholes. Maybe you listen to a podcast on wormholes. There are all sorts of ways you can do research, and most of them are available online. And as you're reading, you should also be like, hey, this is a paper I absolutely need to talk about. For example, in my presentation, I knew I absolutely had to talk about the Greaves paper, because that is the paper that was like, hey, there might be phosphine on Venus. So I absolutely knew that I had to talk about the Greaves paper. You should also be like thinking about what sort of like things need to be highlighted, like the graphs that I used. When I saw a graph about the detection of phosphine, I knew that had to go into the presentation, because that's an important graph. So as you're doing research material, you will automatically in your head, you will be like, okay, this material is important. I should put it in my presentation. This figure or this graph is important and it needs to be in a presentation somewhere. Once you do your research, there will be a second phase called collation. And the collation is where you basically sort of construct a rough outline of your presentation. Now you will pick up exactly what subtopics you're going to talk about. So for my presentation, the subtopics I was going to talk about was possibility of life on Venus, why phosphine is a detection of life, the discussion of Greaves paper, specifically how they figured out that they detected phosphine, and finally the talk about Linkowski paper, their rebuttal to why it was not phosphine. So I had basically 4 subtopics, and that was my rough outline during the presentation. And this rough outline I had already done in my head before I had even made a speech or even constructed my first slide. I had already made this outline. So you sort of estimate the number of points you want to talk about, because generally you do like one point per slide or 1 point every 2 slides or so. Then once you've figured out exactly what you're going to talk about, then you only focus on the material that is important. Okay. So I didn't have to talk about, like, for example, I never discussed in detail about the atmosphere of Venus. Why? Because it is not particularly useful. All you need to know about the atmosphere of Venus is that it's not supposed to contain phosphine. All right. I did not go into the detail about the construct of Venus. I did not talk about like the astrophysics of the planet itself. All of that I did read about, but none of that is really important in the presentation. So you only select the material that is most relevant for your presentation, but you can only do that once you actually have a good, like a rough outline of what you're going to talk about. Once you select the relevant material, you go through them one more time, and then you flesh out each point. Okay. So is there life on Venus? Okay. How do I talk about it? Then I talk about, okay, in the upper atmosphere, there is going to be low temperatures and low pressures, which are more conducive to life. And then when we're talking about biosignature, I have to explain why phosphine is a biosignature, why phosphine is not found on terrestrial planets, and how we know that it is produced by biological activity by talking about how it's made by anaerobic bacteria. This is the way I flesh out my point. Okay? And then as you do this, you're also constructing your speech. Now, some people make the slides first and then make the speech. I tend to make the speech first and then make my slides, but this is going to depend upon the person doing it, right? But this collation period is roughly when you basically summarize everything that you're going to talk about and you make a speech. Then finally comes construction, and this is where you make a PowerPoint. You sort of estimate the number of slides, and generally, if you're going to talk, generally the estimate is you have one slide every 2 or 3 minutes of your talk. Okay, roughly one slide covers every 2 or 3 minutes of the talk. We do not count the title slide or the thank you slides or slides like that. So let me just go to my slides over here. I have a total of 12 slides. I do not count the title slide, and I do not count the thank you and the reference slide. So that gives me 9 slides in total. 9 multiplied by 2 is about 18. So that's a roughly 15 to 20-minute talk right there. So this is one way you can estimate how many slides you need to make. So for a 20-minute talk or so, most likely you will have to make anywhere between, I would say, between 7 to maybe 12, 13 slides. If you're going all the way to 30 slides, for example, if you're making 25 or 30 slides, then that's too much. Okay, so this should estimate, so you should get an estimation for the number of slides. Each slide should always have a specific topic. You can have one topic across 1 or 2 slides, but generally you decide on a topic for each slide. Then when you construct, you put in the material, you put in the text, you put in the graphs. If you decide to put animation, you put some animation and things like that. And finally, once you make your slides, you again revise your speech. Okay, maybe your speech is too long, your speech is too short, so on and so forth. And there's one more point which I haven't put over here. And after that is that you actually practice. You have to practice your speech at least once. You need to make sure that you are within deadline, and you need to make sure that it sort of flows properly. Right? So this is basically a very rough, very sort of holistic summary of how you're going to make, how you prepare for a presentation. So any questions on these, on this thing so far?
No, sir.
No questions? Okay, just give me a second. So now I want to talk just very briefly about how I made my this presentation. Just to give you an example. First thing I would do is I would so I have to detect phosphine in the Venusian atmosphere. First thing I would do is you would probably go to Wikipedia and then do something like phosphine detection. Wikipedia is a good place to start, but that should not be where you stop. If you make a presentation and all it seems is like you just copied material from Wikipedia, I'll just fail you. You should not just stick to Wikipedia. There's a lot of useful information on Wikipedia, okay, but that doesn't mean that you do detection of phosphine. Now, one thing on Wikipedia is the entire material about the paper I talked about is only 1 line, so this is not going to help. So what I do next is I go to Google Scholar, and the first thing I would do. So you go to Google Scholar over here. The first thing you do is you would actually look up the paper or the material that you're going to talk about. So in my case, it is Greaves, Venus, phosphine. So I just put in the keywords. And here we go. Here's the paper. And usually there's this thing on the side will even give you a direct PDF link. So we let it load, and instead of waiting for it to load, you can just see it here. And this is the paper that I get. Okay, and at least for my case, I actually read through the whole paper. You have to read through the relevant material once because I had to know what is important and what is unimportant. And if you look at this, this is a pretty long paper. Okay, I obviously did not talk about every page on this paper. I only took the material that is important. For example, the material I took is this graph, which you noticed. This is the graph of the initial phosphine detection, so it's important. Then I took this graph. This is the graph of the detection from ALMA, so that is also important. I did not take this graph because this was not important. I never even talked about this in the presentation. So when you read the material, you'll automatically know what is important, what is not important. This graph talks about the sulfur dioxide contribution to the detection. Important. So again, it goes into the presentation. This graph tells about the creation and destruction rates of phosphine. Important, so goes into the presentation. And there's a whole bunch of graphs here, none of which I put over there because, none of this is actually important for the material in question. Once I find the graphs, once I'm reading the paper, I will notice various things are being talked about. For example, they talk about the possibility about there being life on Venus. So I asked myself, okay, what are the papers that, what are the papers that talk about the possibility of life in Venus? Because somebody might ask me, how do we know that life can exist on Venus? So what I do, I go back to Google Scholar and then I do a search for Venus life, and then I see if there are any papers for that. And the papers I got was, I think, by Limaye. So, I'll find the life. I will take up the PDF file. And again, we won't wait for it to load. We'll just, yeah. And I'll just pull out the paper like this, and then I'll read through the paper just to see how important it is. Now, in my discussion over there, I actually never talked about this paper, even though I did read it as part of my research, because I realized that the details of this paper is not important. All I did was I talked about the basic idea of why there could be life on Venus. I did not go into full details about this paper. I only showed you on the title. So everything that you do in your part of your research, and I read quite a few papers for this thing. For example, I read some of the other answers, some of the other responses to the original paper, none of which I actually talk about. They all give you a lot of insight on the thing, but not all of them has to go on the presentation. So the collation part, I just culled all of this out, and I only focused on one paper, which is the Linkowski paper. And that's where, again, I go through the whole process of going, okay, this graph, not important. This graph, not important. This graph, this is the one where they do simulation results. Okay, this is important. This goes on the slide. This is the graph where they do the Radiance mixing model. Okay, this is important. This goes into the slide. This is the line dilution. This goes into the slide. The other graphs, all of them, not important. Now, the only way you'll know whether a graph is important or not important is when you actually read through whatever material you're researching, right? So this is the research and the collation bit. I read through all of this, then I make up my points, my basic points. I need to talk about why there might be life on Venus, why there might be, why for pH3, why phosphine gas is important. And then I talk about the original paper, the basic ideas behind the original paper, and then so on and so forth. And that's how I construct my presentation. And at the same time, I'm making a speech in my head. And finally, when I actually make my slides, and you can use Microsoft PowerPoint. If you don't have Microsoft PowerPoint, you can use Google Slides. And of course, Microsoft PowerPoint Office is not free. You need to pay for it. I know there are ways of getting it without paying, but let's assume that you have to pay for it. If you don't have Microsoft Office, you can always use Google Slides. That's what I used to make my presentation. It goes perfectly fine. Of course, you need an internet connection. Let's say you don't have a good internet connection and you don't have Microsoft Office. How do you make a slide? Well, in that case, what you do is you download Libreoffice. Okay, so search for Libreoffice, Libre Office. And here, this is basically an alternative to Microsoft Office suite. It has something called a writer, spreadsheet, presentation, and all of those things. Basically, it has an alternative to Microsoft Word, Microsoft Excel, and Microsoft PowerPoint. It is completely free. All you need to do is download it, and it's like about 300 or 400 megabytes. You need to download it. You don't even have to give you their email address, and they won't put any ads or anything. It's completely free. This is the Office suite that I use. I actually don't use Microsoft Office on my computer, and it works perfectly fine. And any presentation you make in LibreOffice, you can save it as a Microsoft PowerPoint document. So it is compatible, right? So so it is quite possible for you to make a PowerPoint presentation. You can use Office, you can use LibreOffice, or you can use Google Slides, right? And Google Slides, by the way, also work on Android phones. So if you really want to do it on your mobile phone, you can. So once you make your slides, you sort of ask yourself, okay, one topic per slide. So here I only introduce the paper. That's my one, like the whole idea is I only want one idea per slide. So here I introduce my paper. Here I talk about the commotion the paper makes. Here I only talk about like why Venus might have life and why phosphine is a detection of life. I kind of collate them two together as the same idea. Here, this is only for the, here I only talk about the JCMT, the detection they made from the first telescope. And while it doesn't look like it, this is actually an animation slide. So it looks like this, okay? So everything is in one slide. The next slide is only information from the ALMA telescope. Then here is only information about the phosphine creation and destruction and the final conclusion of that paper. So again, it's very, very limited ideas per slide. Here I talk about, I go into detail about the absorption spectrum. Again, this is an animation, as you can see. And then here I only talk about the Linkowski paper. Here I only talk about the results of the Linkowski paper and so on. So you only want one or two limited ideas per slide. You don't want too many ideas in the same slide, and you want to sort of arrange them all together. You may use animations like how I've done over here. Here I use animations, but that's not necessary. Okay, any questions so far?
No, sir.
No. All right. One thing I will show is I found this rather nice presentation here about how not to make a PowerPoint presentation, which I think is very useful information. So I'll just briefly go through this. This was not made by me. I actually forgot who made this, but this is pretty nice. So one thing you should not do in a slide, do not put too much text in a slide. Look at all of this text. Oh my God, nobody wants to read all of this. Nobody wants to sit and read through all of this text. So keep the amount of text in the slide very, very small, or keep it unimportant, right? Next, don't use weird color combinations. This thing just hurts my eyes. It's probably hurting your eyes, so I'll move away from this. But don't use crazy color combinations. If you are either use a dark background with light text, like white, like dark background with a white text, or use a light background with a dark text. Okay, don't use some nonsense like this. You're just going to annoy people, and you're going to annoy me, and I'm just going to give you less marks because of this. I had to stare at this for like 20 minutes. Next, don't clutter things up unless there's a reason for it. There's just too much information at all over the place. And another thing is, there are animations. You can do animations from Google Slides. You can do animations from, PowerPoint or whatever you're using. And I have used animations, as you've seen, but please do not overdo the animations. It gets really, really, really annoying if you have to sit and watch every animation. So it's okay to use a few animations. It kind of helps, but it gets really annoying if you overdo it. Okay, so do not use too much animation. It's just like wasting time. And make sure that if you're putting a picture or a video or a GIF on a presentation, make sure it actually runs. Okay, don't end up like this. All right, I will put this on in the student group so you can have a look at it. But there's some pretty good ideas of what not to do in a presentation. For example, here you notice there's way too much text, but I never actually talked about these. I only talked about the topics here. I never talked about the abstracts. So even if you're putting too much text, make sure that's unimportant, right? Or if you're putting too many things together, make sure that it has a purpose. Here, the reason I cluttered all of them together is because I'm trying to show how much, how much commotion that original paper was making, right? I'm not making you read each and every one of these headlines. I'm just trying to give you an idea that it caused a lot of discussion. In usual, I try to keep my slides simple. It's just a few figures. You'll notice that when I actually talk about my slides, I have very little actual text on the screen. It's just the graphs and the figures going on and the credits for wherever I got them from. Most of the material that I want to present to you, I talk about it. I don't show it on the slides. And one of the worst things you can do is put a lot of text on the screen and then look at the text and then read it out really slowly. That is not a good thing to do. A lot of people do that in presentations. Please don't do that for your presentation. It's not a good look. All right. Okay. So this is my sort of the advice I can give about making a presentation. I am not an expert in making presentations. Like I said before, I'm very, very average at it. maybe even below average. I have seen people make wonderful presentations which are way beyond what I can do. But I think at the very least, I am competent enough to make a reasonable presentation. So hopefully this would give you an idea of what, of what to do. If you have any questions about making a presentation or collecting materials or things like that, you can ask them now. Any questions?
No, sir.
No? All right. There's going to be one last topic of discussion, and that is evaluation. So you are getting marks for all of these. Each one of you are getting marks for your presentation. The evaluation is split up into 4 parts. The faculty is going to evaluate you. Your classmates, not just classmates, but every other student in the department is going to evaluate you. You are going to do a self-evaluation of yourself and your group members. And finally, your attendance is going to count towards the evaluation. So here is just a brief form about what happens. So for those who are not giving the presentation, you're going to be watching your classmates present. And at the end of the presentation, you will all be sent a Google form. And then here you have to evaluate the presentation, like how the presentation was organized, whether it was clear, whether it was logically arranged, whether it was, whether it was concise, whether it was within the time frame, the content of the presentation, whether the presenter understood what he was presenting about, whether you could easily follow what the presentation was about, the visual content of the presentation, it was easy to read, the graphics were fine, things like that, the delivery, all of that. This is going to be done by everybody who's not doing a presentation, like every student who's not doing a presentation. But after that, you are also going to do, each person in the group, after your presentation, you're going to do something called a group self-assessment. And this is a very, very important thing because your marks are going to depend on this pretty heavily. See, because when you make a presentation, there are 3 people. Yeah, and then you're going to split up the duties among all of them. It is quite possible for one person to do all the research, one person to make the presentation, and one person to do the collation and to do the presentation, to actually give the speech. So when I look at, if somebody decides to break up their work into that ways, I see only one person presenting, I have no idea what the other 2 people did. So this group self-assessment form is where you talk about what you contributed to the project and what you think other people contributed to the project. All right. So you'll all get a form that looks like this. I'll just put some junk data here. And for every member of your group, you're going to have to talk about what you think they contributed to the project, whether they contributed to research, whether they contributed to collation, whether they contributed to construction, right? Then you will give a rating for them, how the participation was, how the time management was, what the participation was, time management, what the attitude was, whether they were prepared, whether they were not prepared, things like that. You're going to then rate your group mate. And then you're going to talk about what contributions you made. If they created any problems in the group, you're going to talk about that over here as well. And you're going to put any additional comments here. Now, I'm going to say this now. This form is only going to be seen by the teachers who are evaluating. We will never talk about what actually goes into here to any of the students. Okay? So I'm not suddenly going to go, you know what so-and-so wrote about you in the form. That's not going to happen. The forms are going to be completely anonymous. The only people who are looking at the forms are going to be the people who are evaluating, so the faculty members. Okay? So you're going to evaluate all your group members. Let me just fill this up. So the first group member, the second group member. Okay, and then you're also going to do something called a self-evaluation, where you're going to talk about how much you contributed to the project, which category you contributed the most in, whether what you thought of your behavior towards your project, whether you thought you participated well, whether you thought that your attitude was good, was bad, was better than average, what contributions you made to the group, whether you think you caused problems to the group, and what steps you took to improve them. You need to fill up all of this seriously, all right? And then finally, we have some general feedback that you can give. A detailed explanation of exactly what each topic talks about and all of that. I have a document here which will sort of explain all the details for the rubric, what each topic means, what each point means. So you can just read through it while you're going through the feedback form. And then I've given some examples of how you can talk about it. So the importance of this form is if only one person is doing the speech and two other people are doing stuff like research and collation, this form is how you use to explain exactly who did what. So this way we can properly sort of gauge the contribution by every member of the group. Because it is very, very common in a group project for one or two people to do nothing and for other people to do everything. So if that happens, you can use this form to say this guy did nothing. All right. And that's how and then this way we can like sort of distribute the marks appropriately. Just because you're all in the same group does not mean you're all going to get the same marks. We will be using the self-assessment form and the assessment form of everybody else to individually distribute the marks. Okay, questions?
Is it compulsory for all the three members to speak?
No, this is going to be an internal decision between the group. You can have only one person speaking. As long as everybody is contributing to the group in some way, you can only have one person speaking. The most important thing is, at the end of the day, all of you have to fill up this self-assessment form where you actually talk about what the contribution is. See, you are not the only, you're not the only person saying, I did this, I did this, I did this in the form. Your other two members of the group are also saying, hey, I think Subayu did this, and I think Subayu did this. Okay, so you may write whatever you want about your contribution, but the other two group members have to agree that that is the contribution you did. All right?
Yes, sir.
Okay, any other questions? Ganesh had a question, which was, do we know about the rating of a presentation? You will know it only at the end of the semester. Like after all the presentations are done.
So my question is pretty useless, but what if everybody gives 100% on everything then?
You need to read through the form. I've explained what happens when, I've explained why that's not possible. Okay. Just to make it clearer, where's the document? See, the default mark is going to be 2. That is an equivalent average effort to the group average. See, if everybody gets 4, 4, 4, the average work of the group is, I'm just going to reduce it down to a 2. See, you have to estimate, like, let's just take participation, whether the person is on time and whether they're, if the group has a meeting, whether they're attending the meetings regularly. If everyone is attending the meeting on time, then everybody gets a 2 because that's the average group effort. But if someone is not attending the meeting at all, then they get a 1 because that's less than the group average. But that's if someone is not only like attending the meetings, but they are going through the effort of creating the meetings. They're there like 10 minutes before. They have like a little, they have their Google Meet set up and ready. They have a little graphic that shows like what they want to talk about the meeting. They're sort of leading the meeting and things like that. Then you'll be like, hey, we did like an average amount of effort, but this person did a lot more effort. So you give them a 3. See, if you give everybody a 4, I'm just going to be like, oh, okay, that's just the average effort of the group. I'll just reduce it down to a 2. So yeah, I know like everybody wants to give highest marks to everyone. I'm not going to believe that. The rubric is self-correcting in a way that if everybody gets high marks, I will automatically know that I just need to average it down.
So be very honest with that.
Yeah,
Okay.
just be honest. At least in the self-evaluation, be extremely honest because your marks are going to depend on it. The rubric that you have, it is specifically made to counter the fact that people will try to give high marks to all the group members. So you need to be, we are like, there is an internal system that I'm not going to talk about, obviously, but it's there.
And what if the vice versa happens? Like I give low marks to everyone except me then?
Well, the other two people have to agree with you, no?
Okay.
I mean, if your group hates you, then there's probably a reason for it. And that reason is probably because you didn't contribute enough. Right? Any other questions?
And in any group, if 3 of you want to speak, it's good.
Yeah,
Okay,
yeah,
it's not like always every one person has to speak,
yeah.
because the two persons behind the curtain one day they may have to give, a solo presentation.
Hmm.
Okay, so never feel shy.
Like I'm giving the groups the freedom to decide exactly who's going to do
Hmm.
what. But if
Yes.
you want one person to do, like, if you want to divide the presentation into three parts and one person talks about each part, let's say your presentation is on, oh, give me a topic, give me a simple topic. Let's say a presentation is on something simple like, my mind's drawing a blank now.
Computer.
Let's say it's on wormholes, okay? One person can talk about Einstein's paper on wormholes. One person can talk about like John Wheeler's work on wormholes. And another person can talk about like modern work on wormholes, which is done by Kip Thorne. So you can always make like each person in group focus on different aspects, and each one of them gives a presentation. Or you can make each person focus on like various things, and then one person gives a talk. I will let the internal dynamics be a decision of the group. You can have one person do the presentation. You can have another person answer the Q&A. That's fine. The whole thing is, at the end of the day, each person should make some equal, like the contribution from each member of the group should be equal. And back in this rubric details that I'm going to share with you, at the bottom, I have something called examples, where I actually talk about the different ways in which people might distribute the presentations and how you're going to represent that in the form. So for example, here I have three people, one who's doing only research, one who's doing only collection, and one person who's doing only the presentation, like the construction of the thing. So for each one of them, the person who's doing all the research, for example, does 100% of the research over here, but 0% of the collation and the construction. The person who's doing the speech does 0% of the research and the construction, but they're doing 100% of the collation, the speech, and like the summary of the materials and things like that. And the person who's making the presentation is doing 0% of the research and the speech, but 100% of the presentation. So I have a few examples here that you can look at so that you know how to fill out the form. All right.
Yes, sir.
Okay. Any other questions?
No, sir.
All right. The first groups here, the Sudarshan and Curie groups. So that's Ajit, Neha, Shravan, and Curie would be Adesh, Kushi, and Nachum. You guys need to start working on what topics you want to present on, because your deadline is in 4 days, as you can see. The presentation is in 1.5 weeks, so you have some time. We are giving you 1.5 weeks to prepare, but your deadline for the topic submission is in 4 days. It has to be done by, that's next Wednesday. Yeah, next Wednesday morning. Okay. So I'd advise you by this weekend to at least have one meeting and then figure out, sort of roughly figure out what you all want to talk about, and maybe figure out how you're going to distribute your duties. Okay, I think
Sure,
I'm done,
sir.
sir. Sorry, Sean. Okay. So,
Nothing, sir.
okay. So, Mike, sir, I think I'm done. Do you have anything to add?
No, sir, I don't think anything else. And it's request to all the groups, please send the abstracts before the deadline.
Yeah.
Okay, because if you become very casual with these things, at the end of the semester everyone will be hampered. We are very strict on time. Okay, in spite of everything we are adding this thing for your own benefit. Okay, so please be very responsible, don't delay the things, and yeah, best of luck. And mark my words, after you graduate from here, this thing will really help you. This group
Oh,
dynamics,
yeah, you're all
everything
going to do like
really
some sort of
comes.
presentation in your life. Yeah, it's going to work.
What sir said, that I can end with a small experience of mine when I was a B.Ed trainee in 2017. So one of our ma'am, she used to encourage these classroom interactions. So one day she said that I'm going to teach multiculturalism. That is a multicultural thing that is present in almost all Indian classrooms, isn't it? Even you see in your department, you're from different cultures. Maybe you're from the same region, but due to some dialectal differences, people from different cultures are there in the class. So how to cater the needs of those students? So ma'am said that, okay, next class I won't be teaching anything. 3 or 4 of you can explain your share your experiences. So I remember that next day 3 of us could speak. One girl was Preeti, she was also a would-be teacher. Then I spoke, and then the third person who came, he's a very experienced teacher, but I saw that he was, he got very nervous. His hands were trembling. He was sweating profusely, and then he said that, see, I'm not comfortable talking in front of a huge crowd. So we said that, how come are you, into this profession? It's been a long time. He said that, no, no, no. Whenever I teach, it happens all the time. Okay, so that day I realized that these things should be developed from a very early age. Else later on, when you would be in a profession, years later, still you will see that you're not comfortable with this thing. Okay, and then adjusting with the groups, and yeah, how to digest criticism. Okay, not always people will attack you, but the questions, many people, they don't take it correctly. They take it, I mean, very personally. Okay, so this thing is also very important. So best of luck with this, and I hope that you all will do well. Okay, thank you, everyone.
Okay. Just to add to what Sir said about being nervous in front of a crowd, yeah, it does matter, especially if you're looking to take a position of management where you have to manage other people, which is generally like a promotion type thing. If people think that you're nervous in front of a crowd or you're not confident in front of a crowd, they will automatically assume, it's a psychological thing, they will assume that you are not capable of being a leader. And if you ever want to get promotions in a job where you have to be in charge of other people, they are going to deny you that promotion just based on the fact that you might not be a capable leader. Okay, so it is so one of the things that people kind of judge in a presentation is body language, whether the presenter is looking at the audience, whether like how confident they look, what their posture is like, things like that. Obviously, on an online presentation, because of COVID, we can't judge that. But confidence and body language actually are parts of judging a presentation. So just keep that in mind as well. But we have a limitations this time. Okay, I will forward the sample abstract that I made, the explanation of the rubric, and also the what not to do presentation. I'll put that in the student group, so please have a look at that. Make sure you go through all of this before your presentations, and that's it from me. If you have any other questions, I will take them. Otherwise, you all can log off.
So,
Yes,
so do we have to present with our camera on or camera off?
camera on. I presented with my camera on.
So, but
How am I going to how will we judge your confidence if you can't see your face?
so but
Of
what
all
if
people,
my like
Durga, you
so my
cannot
desktop
make
doesn't have a camera, sir?
use your phone. How do you think I'm using? I'm using my phone as a webcam.
Oh, okay, sir.
Look up DroidCam, DroidCam. Look up DroidCam. It is an app that you can connect to, which makes you use your Android phone as a webcam. That's what I've been using. I don't have a webcam either.
Okay, sir.
Okay. If there are any other questions, I'll take them. Otherwise, you guys can log off.
Sir, whom are we supposed to submit the abstract, sir?
Abstract will go to an email. It is on the. Hold on. Let me. The email is right here. Okay. Can you see it?
Yes.
Okay. So go on. It's on the student presentations thing. Please make sure you've read all of this. This is actually important. So the abstract goes here.
Thank you, teachers.
All right. See you, Adesh.
Thank you, teachers.
Thank you.
Thank you, teachers.